Hello. The message I'd like to convey to you today is that stars in the late stages of stellar evolution are capable of producing large quantities of complex organics, and they travel across the galaxy, and some of them may have reached the early solar system. And for a typical star, when they get old, they become larger and more luminous. For the sun, it will be about 3,000 times brighter than it is when it's in the last 1 million years of its evolution. For a star which is several times the mass of the sun, it could be up to 30,000 solar luminosities. What we are going to talk about today is that at this peak of luminosity, they develop a very strong stellar wind, which are capable of removing most of the stellar envelope. And when the core is exposed, the star evolves to the higher temperature. And when the temperature of the star reaches 30,000 degrees, the ultraviolet photons are capable of photoionizing the previous ejector and therefore forming what we call a planetary nebula. The transition time from here to there, which we'll talk quite a bit today, is so-called protoplanetary nebula phase. This period is about several thousand years. Okay, so we already heard that there are over 170 molecules in the solar space. Over 60 of them are known to be produced by these luminous, what we call AGB stars. They include different kinds of inorganics, organic rings, chains, and black holes, and so on. Now, at the same time, they also produce a lot of solids. And from infrared spectroscopy, we know that over 4,000 stars, or these AGB stars, are producing amorphous silicates, as evidenced by the 10 and 18 micron emission features. And for carbon-rich objects, there is silicon carbide, which over 700 stars have been discovered to show this kind of solid-state structures. So at the same time they're producing molecules, they're also producing a lot of solids, at least inorganic solids. Now, when they become a planetary nebula, then these are very easily identified because they are very bright in the optical part of the spectrum, and these objects have been studied for over 200 years. Now, what is interesting now is that we know that these planetary nebulae, in fact, also are producing complex organics. And that came as a surprise with the NGC 727, which is a young planetary nebula, were found to have emission features at 3.3, 6.2, 7.7, and 11.3 microns. Now, it is possibly identified these features are due to stretching and bending modes of aromatic compounds. So they are either CH stretching or carbon-carbon stretching, and so there is absolutely no doubt about this identification, as these features, these modes are well known by laboratory spectroscopists. Now, what we are interested is if on the asymptotic giant branch there were absolutely no signs of complex organics, then when, at what time were these organics beginning to be manufactured? So we look at some examples of young planetary nebula, then you can see that these features are already present. So we know that they occurred very early in the formation of planetary nebula. Now, but at the same time, we have an evolutionary gap between the end of the asymptotic giant branch and the beginning of planetary nebulae, so-called missing link in the stellar evolution. So in order to have a more concrete observational basis on when do these organics form, we have to try to identify those objects. And Bruce Rifneck and I have been able to discover about 30 of these transition objects. They are called protoplanetary nebulae, which the name is not is probably a source of confusion with young stars, but nevertheless, that's what you use them for in the astronomical community. These objects, I want to emphasize, they have absolutely no emission lines because they are not photoionized. So although the pictures look like planetary nebulae, then all the visible light that are coming from these objects are from scattered starlight. Okay. Now, as soon as we took some infrared spectra of these protoplanetary nebulae, we found the same kind of aromatic features present. So there's no doubt that aromatic compounds are already being made during this transition phase. Now, today I have no time to talk about these unidentified features, so I just leave them out. But you can see the well-known aromatic features are present in the spectra of protoplanetary nebulae. However, they are not the same. They are not the same as spectra in planetary nebulae. Specifically, for example, the outer plane bending modes, the outer plane bending modes, which occur around 10-12 micron, in those regions, there are features that indicate that the rings are not extensive. They are maybe 1, 2, 3 ring system, islands of rings, and not a very extensive graphite-like kind of structure. So you can see these features are only present in protoplanetary nebulae and not in planetary nebulae. At the same time, there is also a very strong 3.4 micron feature, which is definitely identified as stretching modes of antisymmetric or symmetric stretching modes due to methyl and methylene groups attached to the aromatic rings. So it shows that this is the 3.3 micron feature, and that's the 3.4 micron feature. And so now, this is an example. You see this young planetary nebula. The 3.3 aromatic feature is very prominently present, but at the same time, you have these aliphatic side chains, which are seen to be attached to the aromatic rings. So now another third element, which is make the protoplanetary nebula spectra different, are the presence of the emission plateaus. There are very strong emission plateaus around 8 and 12 micron, and these we interpret to be due to the fact that these probably all kinds of aliphatic chains are attached to the aromatic rings. They are dirty, all kinds of impurities. And since most of these aliphatic chains, some examples are shown here, they all have in-plane bending modes around 8 micron and out-plane bending modes at around 12 micron. So collectively, they superimpose to become a broad emission plateau feature at 8 and 12 micron. So a schematic is shown here to illustrate what we mean. So here you can see that. Again, ignore these unidentified features. We can see the 8 micron plateau and the 12 micron plateau, which is present together. And in fact, you can tell that a lot of the fluxes are emitted in these plateaus in addition to the features themselves. Now, so what is the compound? I mean, there are a variety of examples that have been known in the laboratory. They have a mixed aromatic aliphatic structure. If you have a pure hydrogen-carbon system, there may be a hydrogenated amorphous carbon, and this model was promoted by Walter Dooley. And there have been also suggestions of kerogen-like structures. For example, in this schematic of a kerogen, we have small islands of aromatic units, which are shown in dark, and then they are connected by all kinds of aliphatic chains. And you look at the spectra of coal. This is the work done in France in Saclay group. They showed 8 and 12 micron broad emission plateau features. At the same time, you compare the 3.13 and 3.4 micron feature in planetary nebulae, you see there are a fair amount of similarities there. Dr. Cadello, I understand he's also have a poster in this meeting, and look at the similarities between petroleum fractions in comparison to the spectral protoplanetary nebulae, and there's again some similarities. So I don't want to draw too much conclusions in there, except to say that we're definitely looking not in a pure aromatic compound, but compound with extensive aliphatic structures, and at the same time, they probably have other elements of impurities present, like oxygen, sulfur, nitrogen, etc. Now, the first clue that something is happening is the detection of acetylene in a very old stars. And then we look further there at diacetylene and triacetylene, and we look at the qualitative picture of evolution. It seems the first step is that we have acetylene, which they close together to form benzene, And the interesting thing is that we know the time scale. Over about a couple thousand years, they cluster in form of aromatic rings, but probably have all kinds of junks attached to the rings. And in planetary nebula phase, which have a lifetime of about 20 or 30,000 years, the onset of photoionization probably break out some of the chains and close some of the rings and so on. Okay, now I want to emphasize one point is that here, because we know the time scale of evolution, both from dynamical and evolutionary basis, that we have a very well determined laboratory. So we know the physical conditions, we know that it's only a single energy source with simple geometry. So all the reactions that lead to the formation of these aromatic aliphatic occur over time scales of hundreds of years. Now, how do they form? Theoretically, no way they could form. I mean, it's just theoretically impossible. But they do form because we see them form on the time scale of hundreds of years. Now, some of our astronomy colleagues have always said, oh, wow, it's very interesting. You find all these solids forming in stars, but they don't matter because as soon as you eject them into the interstellar medium, they'll be destroyed by radiation field and shocks and so on. But now we know that is not the case. For example, for isotopic studies, we know that the stellar grains that reach the surface of the Earth in form of silicon carbide, which I mentioned before, is a common element in stellar grains. And if you look at IDPs, and they also have 3.4 micron feature, which is very similar to the ones that we are seeing in protoplanetary nebulae. In carbonaceous chondrite, they have complex organics similar to kerogen, which is called IOM, and they are, again, in terms of structure, similar to what we are seeing, even on Titan, in the atmosphere of Titan. So we now think that the planets formed by things being aggregated together, so it is a possibility that some of the remnants of stellar material which have been ejected by these stars and planetary nebulae travel across the galaxy, embedded in the early solar system, and form part of the primordial material that in the early Earth. Now, if you look at the numbers, they can produce 10 to 28 kilograms of stardust per year in the galaxy. Well, I don't know what's the efficiency of reaching to the solar system, but we can do a comparison with this is a model of the IOM by Doreen and Robert. I think she'll give a talk on this Thursday. You can see an illustration of mixed aromatic aliphatic structure of a disorganized manner, amorphous grain, and they are very similar, in my opinion, to the kind of grains that we're seeing being produced by planetary nebulae. So in summary, I just want to say that development of infrared spectroscopy have allowed us to detect the stretching and bending modes of complex organics, and they have, we can see by looking at objects at different stages of cellular evolution to show the chemical changes in structure as a sequence of time. And we know that in this low-density circumstellar environment, over time scales of hundreds of years, we see starting points of simple molecules like acetylene all the way developing to aromatic and aliphatic units. The detection of pre-solar grains suggests that these grains can indeed survive the journey through the Milky Way galaxy, and we look at the macromolecular organics in meteoroids, IDPs, comets, planetary satellites. There may be a fair amount of similarity in terms of chemical structure. So the interesting question is to what extent our early Earth have been contaminated or enriched by stellar ejecta, which are producing large quantities of complex organics at the end of the star's life. Thank you very much.